Hello, thanks for making efforts to listen this video. I am Wenjiang, a fourth-year PhD student from Texas A&M University, Corpus Christi. Our paper is talking about joint optimization of node placement and UAV's trajectory for self-sustaining air-ground IoT system. Today, we will have 5 sections. We will first introduce some backgrounds and our research work related to this paper to motivate our today's research presentation. And then we will introduce the system model of this paper. After that, the proposed algorithm will be illustrated. Finally, we give the experimental results and conclude the contributions of this paper. So let's dive into the introduction. As we all know, IoT devices increase with an incredible rate. Based on this picture, connected sensors will arrive at a trillion level. However, because those devices are powered by batteries, those IoT devices suffer from limited lifetime and high maintenance fee on recharging and replacements. In this background, energy harvesting technology is a promising solution to address these issues. IoT devices equipped with an energy harvesting module harvested renewable energy from natural sources, such as wind and solar. Through this way, self-powered IoT devices is proposed. That is a promising technology to realize the sustainable IoT system. However, due to intrinsically weak and unstable power supply, energy harvesting IoT devices work intermittently. As the right side of slide shows, in traditional battery-powered IoT system, all devices have a stable power supply. Therefore, the battery-powered devices have sufficient energy processing. The transmitter and the receiver can communicate at any time. For self-powered devices, because we could never know power intensity in advance, there is an uncertain energy status of self-powered devices. Second, due to the weak and renewable power supply, self-powered IoT devices have a very limited capability on processing. Due to intermittent work pattern, different from the battery-powered IoT devices, that the transmitter and the receiver can wake up at any time, while one self-powered IoT device transmits the data to the other device, that device might be sleeping. Therefore, the synchronization of energy availability for self-powered IoT device has to be considered. So, we can conclude that the routing and the energy allocation policy for the traditional battery-powered devices are not appropriate for the self-powered IoT devices. Therefore, in our previous work, we developed a system to collect data sustainably by optimizing the energy allocation and routing policy. As this picture indicated, we deploy a set of self-powered IoT devices in an open area. Those devices with 3 functions: sensing data, transmitting data to sync through multi-hop. Also, devices can forward data for its neighbors. We aim to maximize the amount of data delivery to sync through optimizing the routing policy and the energy allocation on sensing and transceiving. In this paper, we deploy multiple agents, deep reinforcement learning, to control each device's energy allocation and routing destination, subject to the limited capability on processing and limited energy supply. However, due to the energy constraints and limited capability of self-powered IoT devices, even with an outstanding routing policy in an unsuitable sensor placement, or say an unsuitable topology of IoT network, will result in poor performance of data collection. Let's illustrate this problem with a small case. The left corner shows a simple case of 6 nodes, multiple hop self-powered IoT system. All sensor data by node 1 to node 6 are required to send to sync. Therefore, the node 1 and node 2 not only need to sense its own data, but also has to receive data from other 4 devices, including node 3 to node 6, and then transmit the data of 6 devices to sync. But for the outlier devices, such as node 5 and 6, they only need to sense and transmit their own data to node 3 or 4. Therefore, the energy consumption of node 1 and 2 is dramatically different from the energy consumption of node 5 and 6. Thus, while we have a homogeneous system as the second picture indicated, the energy consumption of devices located far away from sync is much smaller than that of devices close to sync. Therefore, in this paper, we propose to upgrade a set of nodes so as to build a heterogeneous system. The upgraded node would have a larger capability on harvesting energy and storage. However, because only a limited number of nodes close to sync, even all nodes that is 1 hop away to sync are upgraded, the improvement in large-scale network is not obvious. Thus, we can further dispatch UAV to collect data from upgraded nodes. So in this case, the normal node can transmit their data to the upgraded node, and then the upgraded node can transmit the collected data either to UAV or to the sync. To realize such a heterogeneous air-ground integrated system, we have to answer 3 questions. First, which nodes should be upgraded? This is an MP problem. Second, which nodes should be visited by UAV? UAV could never know which nodes have more data waiting for collection. It is highly possible while UAV visited the node, that node do not accumulate any data for UAV collection. In this situation, UAV's energy is dissipated. Finally, UAV also has a limited onboard energy. It has a limited flight duration. So we are not sure if UAV are able to visit or upgrade the nodes. Therefore, to address these mentioned issues, our key idea is to first pruning the nodes that are located at a marginal area. Those devices only need to sense and transmit their own data. Therefore, they are impossible being the upgraded nodes. Due to the limited energy of UAV, while UAV travels to the last layer, not only UAV costs more travel energy, the data is required to send to the other direction of sync. Thus, it is not expected to be far away from sync. Also, we can prune the nodes at the last layer. After narrow the range of upgraded nodes, then given the maximum number of nodes can be upgraded, we aim to maximize the coverage range and the distribution. Here, coverage range means the number of one-hop neighbors of upgraded nodes. We want to maximize the neighbors of upgraded nodes. The distribution means the upgraded nodes should not distribute closely in space. Through this way, the upgraded nodes are picked up. Then the UAV trajectory can be found by applying genetic algorithm to solve TSP problem. We formulated each individual with a node ID. The sequence of gene represents the visited order, while the potential trajectory cost is out of the maximum onboard energy. That trajectory is not qualified. Therefore, the individual is deleted. Similarly, we evaluated the potential trajectory with distribution score and energy consumption. We aim to minimize the trajectory path and maximize the distributed score. Through GA, we find the near optimal trajectory of UAV. Here indicates our simulation results. Figure 5 indicates our upgraded strategy and UAV trajectory. As we can see, the upgraded devices mainly concentrate on the nearby of sink and the center of deployment area. Because the purple devices that close to sink can transmit their data directly to sink. Therefore, UAV flies to other two devices to collect data. Here, the first picture indicated the results of a system without a UAV assisted. We compare the sync received data while there are different number of upgraded nodes. X-axis means the training episodes. As we can observe, after the upgraded nodes is greater than 9, even we continue to upgrade more nodes, the sync received data won't increase. The right picture compared the UAV assisted heterogeneous system. Because of UAV, while number of upgraded nodes increase from 9 to 12, the sync can receive more data. Specifically, in the left picture, while the master node is equal to 0, that means it is the homogeneous system. So here is our paper. In this paper, we proposed a heterogeneous air-ground integrated self-powered system for data collection. After that, we provided the corresponding upgrade strategy in the heterogeneous self-powered system. And then we optimize the UAV trajectory under energy constraints circumstance. Finally, we show the simulation results to indicate the performance of proposed algorithms. So here is our paper. Thanks for listening.